Hello everyone, my name is Lawrence van der Maten. I'm a research director at Facebook AI Research, and I'm excited to tell you something today about our recent work on private prediction and certified removal. This is joint work with Ani Hanoun, Chuan Guo, and Tom Goldstein. So as an introduction, the question that we are interested in studying in our team is basically how do we protect the privacy of training data in machine learning? And we're working on three different questions related to that sort of core question. The first one is we're working on training models using cryptographic techniques. And we do this in a project called Crypten. I'm not going to talk about Crypten today, but I encourage you to look at our website at crypten.ai or look at the code on our GitHub if you want to learn more about training models using cryptographic techniques, in particular secure multi-party computation. The two questions I will focus on in this talk are how can we safely release predictions into the world? So how can we, after training a model, release predictions publicly and limit the amount of information that leaks about the private training data from those predictions? And the second question that I will try and answer in this talk is what can we do when training data is removed after training the model? Can we somehow update the model in order to remove the removed training data from the model? And in this talk, I will use differential privacy as sort of the core measure of privacy. And so I'll give you just a one-slide introduction of differential privacy. So the idea is, suppose you run a randomized algorithm, typically a learning algorithm in machine learning, on some data. Then what differential privacy says is that changing one data point in that data should hardly change the output distribution of the randomized learning algorithm. And that condition should hold for all data sets and all outputs. And so mathematically, it looks like this. So we are given some data set D, and then we have a dataset D prime that differs in only one example from D. And on this dataset D or D prime, we apply a learning algorithm, A. And that learning algorithm selects a possible output, right? It selects an hypothesis, it selects a set of model parameters from the set S. And now what we want is that when the learning algorithm A is run on dataset D or D prime, that the probability of selecting a particular hypothesis is almost the same for every possible output, right? For every possible S and for every possible data set. And almost the same is specified in terms of this privacy loss term, epsilon, which is a multiplicative term on the probability, and then a privacy failure probability delta, which is an additive term, which allows for a few failures. And this is the measure that we'll use to measure privacy throughout this talk. So in the first part of my talk, I'll look a bit at private prediction. So what is private prediction? Well, the idea is like this. We train a model on some private training data. And now we're going to release predictions for B, capital B, test examples to the world. And now the question is, how much can you learn about the private training data from observing the predictions of these test examples? And that amount of information we want to limit. And we can limit this through differential privacy. If we do that, we get the following definition. So we have some model data that is trained on private data. The private data is again denoted by D. And then we run this model. The model is phi, theta are its parameters. We run it on some test example, xb. And what the model is going to do, right, it is going to predict a class. So it's going to predict a class for the example xb. And we're going to repeat this capital B times, right? We have a budget of test examples. And for all these test examples, we're going to run our prediction, and we're going to release the prediction to the world. right? And so if we want to limit the amount of information that's leaking through these capital B predictions, then we can do that through differential privacy using the same privacy loss and privacy probability failure that we saw before. And so this is the definition that we're going to focus on. And in particular, we're going to look at what happens empirically. How do methods for private prediction perform empirically? And in our study, we look at two types of methods. The first type are private training methods. So the idea is if you train a model in a differentially private way, and so the model parameters don't leak much information about the private training data, then you can release infinitely many predictions using that model because you're never going to leak much information about the private training data through your test predictions. And so it allows us to set capital B, this test example budget, to infinity. The second approach is to do a private prediction approach, which means we're going to train a non-private model. So the model parameters may leak a lot of information about the private training data, and we're going to limit the amount of information at prediction time. And so now the information leakage becomes a function of the budget B. So the private training methods we look at are model sensitivity or output perturbation. And the basic idea is to, after training, add Laplace or Gaussian noise to the parameters. And the goal of this noise is basically to hide information about individual training examples. And you can show that this mechanism gives you differential privacy for linear models with a regularized differentiable convex loss. So under relatively mild conditions, this is working. The second type of private training method that we look at is loss perturbation. So here, rather than training first and adding noise to the parameters after training is done, what we're doing is we add a Laplace or Gaussian noise term to the loss. And we're going to minimize that randomly perturbed loss functions. And this provides differential privacy under the same assumptions. The third method we look at is differentially private SGD. The idea here is that you're going to do learning using stochastic gradient descent. But at every step, at every gradient update, you're going to clip the gradients to have a certain norm. And you're going to add Gaussian noise to that gradient. And what you can show is that this provides you differential privacy. And you can provide differential privacy under milder conditions. So you can do it for nonlinear models as well. But it does require a positive, a non-zero privacy probability failure, delta. The private prediction methods we look at are prediction sensitivity. So this is also an output perturbation method. But here the Laplace or Gaussian noise is not applied to the model parameters, but to the predictions that the model produces. And you can show that this provides differential privacy under the same conditions as before. So for linear models with a regularized differentiable convex loss function. And the second private prediction method we look at is subsample and aggregate. This is a more generic private prediction method. The basic idea is you split the training sets into capital T disjoint subsets. And you train a model on each of these subsets. And now at inference time, you're going to make predictions using each of the models, but you're going to apply the exponential mechanism on the model votes. So each model is going to vote for a particular prediction, but you're going to essentially add noise in selecting the maximum vote. And this provides differential privacy without any assumption. So this works for any type of model. So we did experiments with these methods on the MNIST handwritten digits dataset, where we train our models, linear models using LBFGS or DPSGD for the DPSGD method, which obviously relies on SGD being the optimizer rather than LBFGS. And we use L2 regularization, which is set via cross-validation. And this is quite important in practice because the L2 regularizer plays a role in the differential privacy guarantee. And then the kinds of plots that we get are plots like this. So what you're looking at here is on the x-axis you see the privacy loss. So a lower value means more privacy. And on the y-axis you see the accuracy of the model, where the dotted line on the top is the accuracy of a non-private model. So this is sort of the upper bound on the accuracy that we can get. And I'm showing you two plots. On the left, I'm showing you a plot where the failure probability delta is 0. And on the right, I show you a plot where we allow for a small privacy failure probability of 10 to the power minus 5. And what you see in the plot on the left is that, in particular, the subsample and aggregate method is really quite effective. It seems to work better than loss perturbation and model sensitivity, and definitely better than prediction sensitivity for this particular setting. So for most of values of epsilon of the privacy loss, and for the inference budget that we chose here, which here was set to B's 100. If you compare the plot on the right with the plot on the left, what you see is that allowing for a small failure probability can make the methods much more effective. So note that the scale on the x-axis is changing. On the right, it only goes between 0 and 1. And so what you see is that, in particular, model sensitivity and loss perturbation become way more effective. Suddenly, they're much better than subsample and aggregate. And now we can also use DPSGD, which turns out to work even better than the other methods if you allow for a small failure probability. But there are other plots that are interesting to look at. So here what we do is we fix the privacy loss, epsilon, to 1, and we look at accuracy as a function of the inference budget. So of the number of test examples that we're going to release to the world. And so in these plots, private training methods will be horizontal lines, right? Because irrespective of the number of test examples for which you release predictions to the world, the amount of privacy loss will be the same. But for private prediction methods, you know, obviously the privacy loss and or the accuracy that you get in order to get a particular privacy loss is going to depend on the number of test examples for which you release predictions. And so what you see is that even though subsample and aggregate was quite effective for a small inference budget of, let's say, up to 100 examples, if you're going to release 1,000 test predictions to the world, then suddenly subsample and aggregate is not very competitive anymore. And the same for prediction sensitivity. And this gets even worse if you look at the plot on the right, where we allow for a small failure probability. There are many other analyses that we did, many of which are presented in our paper, which I recommend you have a look at. Here are some examples of things that we looked at. So we looked at the effect of the number of training examples on the effectiveness of these private prediction methods. And then what you see, for instance, in the plot on the left is that subsample and aggregate is very effective when the number of training examples is small. But as the number of training examples grows, methods like model sensitivity or loss perturbation become much more competitive because the amount of noise that you need to add to the model parameters or the loss function depends on the number of training examples that is being used. And so in general, what you see is that there are a lot of trade-offs in these private prediction and private training methods, which we tried to summarize in this table. I won't have time to go over the entire table, but I hope what this table gives you is some sense of like what happens when I change a particular parameter, like the number of training examples n, or the number of classes c, or the ambient dimension of the data d, the number of test predictions b, the number of models that I'm training, as well as the L2 regularization parameter on things like privacy loss, privacy failure probability, accuracy, as well as training and inference time. This was a very quick run through of this paper. I recommend you have a look at it if you want to learn more and if you really want to dive deep into this empirical study. In the second half of my talk, I want to tell you a little bit about our work on certified data removal from machine learning models. So here we look at a slightly different learning setting. So basically the question that we ask ourselves is, if training data is removed, how can we remove it from the model? And so the learning setting we consider is a standard supervised learning setting where we're given some training set D with labeled examples, there are n of them, and we have some learning algorithm A that is applied on the training set D, and it will select some hypothesis. We call it H star here. And now what we want is we want to develop a removal mechanism. The removal mechanism is called M. It takes as input this the original hypothesis, the original model H star, the data set, as well as an example Xi that we want to remove. And what the removal mechanism is going to create is it's going to create another hypothesis, we call it H minus, that basically tries to remove, or is not influenced by this example xy, yi that we want to remove. And so what is the goal of removal? Well, really what we want is that if we train a model on all data and then remove sample I, that is the expression on the left, right? We apply A on learning algorithm A on dataset D, and then we apply removal mechanism M with this example I on the results, right? So we remove the example from the trained model. Then what we want is that the output of that removal mechanism is almost the same or identical to what we would have gotten if we wouldn't have trained the learning algorithm on the example I in the first place. And so this is the expression on the right. This is the sort of ground truth, right? Like where we remove sample I from the data sets and then train on this new data set without sample I, right? And if we do that, then obviously the model does not contain any information about the removed sample I. And this exact removal is possible for some methods. So for instance, if you think about nearest neighbor classification, then you can do exact removal. So you can take the model on the left and you can remove the rightmost blue points. Basically with zero computation, it'll give you, will give you a new model, and the new model will not contain any information about the removed data points. However, for parametric models, which is typically what we're interested in, this is a lot more challenging. And the reason is that if you remove this blue point, you essentially need to retrain your model, right? So with the blue point, you would have gotten solution W star. Now, if you remove the blue point, the only way you can get solution W star star is basically by retraining the model from scratch, which is computationally intensive. So what we're interested in is answering the question, can we do better? In particular, can we be more efficient by allowing for non-exact removal, but still providing very robust guarantees through differential privacy? And so the definition that we come up with is the definition that you see on the slide here, which we call certified removal. And it looks very complicated, but the basic idea is that the output of the removal mechanism applied on the result of the learning algorithm, right, and trying to remove sample I, should be statistically indistinguishable from the result that we would have gotten if we had trained learning algorithm I on the data set, with the exception of sample I. Right? And so if you look at this, this is a lot like differential privacy, right? The data set in the top and bottom, they vary in one example, namely sample I. And we want to say like the probability of a particular output should be almost the same, right? Or the ratio between those two probabilities should be close to 1. And this property must hold for all data sets D and for all possible outputs T. And so, if we can develop a certified removal mechanism like this, then we have a very robust guarantee that models that were trained on sample I, but then the removal mechanism was applied, are basically statistically indistinguishable from models that were never trained on example I in the first place. So we develop a certified removal algorithm for linear models. So we look at sort of standard linear models trained with empirical risk minimization using some L2 regularization. And we assume a convex loss. So basically the learning algorithm A applied on the training set finds the optimal solution of the loss because there's only a single solution. And now what we're going to do in order to do the removal, so in order to remove sample I from this model W star in order to produce model W minus, we're going to do a single Newton update, but we're going to do it in the wrong direction because we want to remove the sample I. And so what this is giving us is, well, not W star star, right? W star star is the thing that we would really want, which is the location where dataset D prime, which is the dataset without sample I, has zero gradients. But it will get us close to it, right? It will get us to this solution, W minus, that is somewhat close to W star star. And you know, what's nice is because we only do a single Newton update, the update is relatively cheap, and so we can get this W minus relatively quickly. But there's one problem, which is that there is some residual error, right? W minus is not the same as W star star. And even though the residual may be really small, it can still leak information about the sample I. And so what we're going to do in order to hide that information is at training time, we're going to apply loss perturbation. So we're going to basically mask the gradient residual with some random noise B. And what this does is basically it makes sure that you know, both W star as well as W star star could have different values, right? Because we don't know what the noise is. And so as a result, W minus becomes indistinguishable from W star star, right? Because it's unclear whether the gradient residual comes from the example I or whether it comes from the noise B. And I'm not going to show you the proof, but what we can show is that this combination of training with loss perturbation and then applying this single Newton update at removal time gives us the certified removal guarantee. And we did experiments with this method on the Alson image classification dataset. And what we're showing here is basically the test accuracy of the model as a function of the number of removals that's supported. The reason why there's a number of supported removals is because we need to sort of keep track of the budgets. We need to keep track of whether we applied enough noise in order to be able to remove more data points from it, right? Because every time, you know, the gradient residual grows a tiny little bit, and so, you know, if we do more removals, we may need more noise, which is why supporting more removals means that you're paying a price in terms of test accuracy. But what's nice here is that, you know, the price that we pay in terms of test accuracy is actually not very large, even if we want to support, let's say, 10,000 removals on this data set, which is a large chunk of the training set. And the removal time is really small. We can remove an example in about 0.5 seconds, whereas retraining the model from scratch would take over 2 minutes. So that's all I wanted to tell you about today. So I talked about private prediction. I talked about certified removal. I also encourage you to look at Krypton if that's something that you're interested in. Again, this was joint work with Anya Noon, Chuan Guo, and Tom Goldstein, and I thank you for your attention.